logics.
All right. Thank you very much for the introduction. I must say I'm very much enjoying this conference. I'm learning a lot about different techniques and different logics and how to approach this. I'm saying this because, I mean, this is my first paper at TABLEAUX. So this is also my first very foray into like hardcore proof theory, I suppose. So I'll first give a little bit of motivation of the kind of problem that I want to solve, and then how I got to a solution, but perhaps there will be lots of suggestions of better solutions. So the main motivation is to use logics to look at systems with distributed knowledge and claims. So we can think of the world as having many different companies and parties that are claiming whatever you want, like whatever they want. But we need to have some way of combining that into a single system where we kind of regard, when we're making a system that is based on claims made by other people, we want to be able to regard them in their proper context. And this proper context will be defined using modalities. Is the tool that I've chosen to use because there's lots of literature that considers belief, time, and communication as expressed by modalities. So in this case, I mean, we can say when and where a statement is given, who said it, who hears a statement, how a statement is communicated. And then in particular, I'm interested in these kind of modal logics that are intuitionistic. So we can, they're inherently constructive and can be adaptable to formalization of, well, I mean, automated and computer systems. Now, the focus of this talk is about decidability and beyond. And we've seen a little bit about it. So in practice, it's good to decide whether a property is provable. So that gives us tools for completing proofs for logical arguments. And if you are a company making statements, it's good to maybe check the consequences of when you make these statements and explore these possibilities. Obviously, decidability is a bit of a difference between decidability and runnability, or by which I mean being able to practically run the algorithm of decidability. So you will get the standard decidability arguments may have exponential blow up, and there's maybe ways to organize data structures to facilitate quick proof steps. But that's still a bit part of the motivation. So it's not like I got there completely. But this talk and this paper is kind of divided up into two parts. First, establishing just decidability. We need to have a framework where we at least know that we can decide whether something is provable. And this is done very, very traditional style by adapting Fanning's cut elimination proof by basically hacking into it and adding more cases to it. And then the second half, if I have time, we can go into the actual forward search proof technique, which is then hopefully will be more runnable or more executable than exponentially searching all the possible proof trees that you would need to discover. And this forward search technique instead will focus on using cuts. So I like the irony of first establishing decidability by eliminating the cuts, and then when actually proof searching, using cuts in their full force, which is quite nice. So what do I actually mean by multimodal K? I need to disappoint some people here. So I'm really focusing on the box-like fragment of K in this instance. So I'm not looking at possibility as a situation. So I'm thinking of modalities which satisfy axiom K in the sense that it was used in one of the previous talks as well, which is the MA implies, or M of A implies B implies MA implies MB. So I'm assuming in general that we'll have some set of formulas, some set of modalities. Then we can use a sequence to say A1 to AN proves B, to say that by assumptions A1 to AN, we can prove conclusion B. And then axiom K and axiom necessity together facilitates this kind of, the admissibility of this kind of rule, where if we have sequence of this form, then we can construct a proof of a sequence of this form. So this is the basis. So every modality will have this kind of rule, which is because of the motivation, we're talking about some kind of domains of knowledge. So we're kind of assuming that each of these modalities are, well, combine, we can combine statements from different sort, like different statements into a single framework. To this, we want to add additional modal axioms that I need. So the types of axioms that I consider are the unitality kind of axioms. So these are all kind of optional axioms depending on which modalities you want to express. So unitality would be if you have something of MA, then you can prove A, which you can consider that M is some kind of domain of true knowledge. So it is actually true if it's true in MA. We can have some kind of subsumption or inheritance, where if something holds in MA, then it holds in NA. And the last one is quite curious, but it pops up in a lot of cases, which is when if MA holds, then NRA holds. So the way that I see this is that modality N sees MA, but not as MA, it sees it as some other statement, sees it as RA. Obviously, we can choose these N and R to be anything we want at this point. So I'm assuming that we have some relation from M to lists over M, where M to this list asserts the axiom MA proves this chain of modalities here. So
sorry, the R is a modality, like
yeah. So these are all modalities. Yeah. So this is just like a general schema of the kind of thing that I'm expressing in the basis here, and so we can think of these all as kind of elaborating what MA means, right? So so I don't know if I go no. So in order to facilitate this decidability, we first have some unrestrictive properties. These are just admissible in general. So obviously M implies M because of, if you have the identity theorem, it should. And we have this kind of transitivity option that if M is some sequence of modalities, and then there's an N, and this N can be elaborated to gamma, then we can substitute this gamma here and get alpha, gamma, beta. So these are the unrestrictive properties, because this last one we should be able to prove if we have axiom K and necessity from the other assumptions. Then the more restrictive properties, in order to get decidability, I want to have this kind of decomposition of the situations when you elaborate into multiple modalities. So obviously, having one formula explode into multiple modalities, that's very counter to decidability, because you don't want to have like an infinite recursive loop when you're looking. So I want there to be a kind of basis for whenever you elaborate into longer chains of modalities. And so I define it as M minus N. So for any two modalities, M and N, define a finite set M minus N, such that, well, if R is in the set, then M implies NR. So each is an instant of an axiom. But then for any non-empty other list, alpha, then if M implies N alpha, then there must be some basis of alpha. So R and M, such that R implies alpha. This is a way to kind of get a hold of these exploding chains of modalities. So we can think of maybe the whole space of alpha, of how N sees M. That can be all kinds of modalities. And then we want to have at least some finite set. And then we need some other property to make sure that this finite set is somehow reductive. So we should have some kind of ordering on modalities, such that all of the modalities in that set should be smaller or equal than the modality that we're looking at. All right, so let's look at some examples. Obviously, we have our familiar box modality. So in that case, we have box A implies A, and box A implies box A. Obviously,
S4 modality.
Yes. Obviously axiom K and M. So the total relation, so this relation is just a total relation because box can be any number of boxes. Box can become box N. And then box minus box, well, how does box see box? Well, as box.
So the turnstile we read as implication or as the turnstile there?
Which one?
Yeah, like say box.
Well, you can put it as an implication at the moment. You can also think them as sequence at this point because I didn't introduce the full logic yet.
Okay.
So at this point, I just write them as sequence, but it should be the same as that. Obviously, you can use box with other modalities. So I kind of think of box as marking stuff that holds in every other modality. So I can think of box A is M box A, for instance. For every modality, we can do that as well. Maybe more general or, well, the kind of axiom scheme that I'm very interested in is maybe when you have a lot of modalities, a lot of spaces, and we have some awareness relation. So we have some reflexive transitive relation where M sees N, which effectively means that if we have NA, then we have MNA. So M sees everything. Whenever you know that NA, we should derive that M knows about it. And we can do that as well. So N can always be unfolded into a chain of modalities that see each other. So in the realm of the motivation that I said, you could have a communication. So if you communicate to someone, then they should be able to see the communication. Or if you announce someone, everyone should be able to see it. And that's the kind of thing you can express here. Now let's go into decidability. Now we have covered decidability already a lot in other talks. So my proof of decidability is very relatively straightforward. Adaptation of Fanning's structural cut elimination proof. So we use Genson's sequent calculus. We need to establish some things in order to get that ball rolling. So we suppose contexts are given by some finite sets. I forgot finite here, sorry. So we kind of structurally have commutativity in there and contraction. And then we write more generally a weakening that is a modal weakening. So gamma can be extended to delta if for every A in gamma, A is in delta, or A was a modal form, whereas there's some MB, or there's some NB in delta such that N implies M. So delta covers gamma in a way. So you have some kind of structural weakening. So if you have a proof of gamma A and gamma can be extended to delta in this way, then we should have some proof of delta A in a very structural way. So this proof should be the same size. So I would even say it's the same proof in a way if you can proof check. Then we use a modal shift. This is very much related to the kind of adjoint operation that you would consider in Fitch-style modal logics. But in this case, because I don't want to have more general context, I immediately resolve this adjoint operation. But which, I mean, just for the people that don't know, all I'm doing at this point is that if we have some context and some modality, I want to extract from gamma everything that is readily provable within M. So M minus gamma, we extract it. That's every A such that there's an NA in gamma and N implies M for every NA. That implies M, we have an A. And for every NA such that there's an R in N minus M, we have RA. And because I had this kind of reductive argument, we have that every formula in M minus M gamma is a subformula of gamma. So the subformula property holds. And we have some general properties. So if gamma can be weakened to delta, then M minus gamma can be weakened to M minus delta. And if M implies N, then M minus 1 gamma. Then, well, N sees at least as much as M. And then the last one, this is kind of the strongest one. So if T is in M minus N, then M minus gamma can be extended to T minus of N minus of gamma. Now, okay, so we need the logic. So just to kind of quick recap, so we're looking at intuitionistic modal logic, multimodal logic, where we just have a bunch of axiomatic formulas, conjunction, disjunction, implication, modal formulas, top and bottom, which we equip with the standard intuitionistic reasoning, plus for the modalities, we want to have these axioms there as well. So this one, the axiom Kn, and that we have an axiom here, which we all and wrap up into a sequence calculus of the following form. So this is Gensen sequence calculus extended to adapt to these modalities. So these are the standard rules, which you may be familiar with. And then here are the additions. So there are two, I separated them, two different steps. So this is a kind of really only to facilitate when you have a unit. So if we know that M can be MA implies A, then if we have an MA, we can always extract an A, unfold it, if we think bottom up. And then here, this is the big one. So if gamma proves, to prove that gamma proves MA, we can do the inverse shift of this gamma. And this calculus has all the kind of properties that you would want. So it has the identity theorem. We have a subformula property that by extending the relational modality such that we have the subformula property. So we know that a proof search of the sequence calculus will terminate by exploring all possible proof trees. And then the second one, for the completeness and soundness, we have the fact that the sequence calculus admits cuts by adapting the Fanning's cut elimination proof. The full proof is in the paper, but just to show one case of it. So for the cut elimination proof, you want to prove, if you have a proof of gamma A and proof of gamma and A proves B, then you want to construct a proof of gamma proves B. And we can, for instance, consider a case where we may have, what is it, M implies N RA and M implies N at the same time. So this N minus 1 inverse of MA will give RA and A. That's the things that are readily available there. So if you want to then cut this, so we want to prove the cut, we need to be able to separately cut RA and A. And essentially, we use the properties of this modal shift operation in order to do this. So we have one where this proof can be, by weakening, can become a proof of A, which then can prove RA to cut the RA. And there's another argument to cut the A as well by unfolding. All right. Now, how much time do I have left? Yes. Oh, sorry. Yeah, I see.
You have 11 minutes.
11 minutes. Okay.
Including questions.
Including questions. Okay, let's do 6 minutes then. So that was an argument for decidability. Obviously, if you implement that, you have to search through all the proof trees, and there is some exponential blow-up. I mean, there's a lot of exponential blow-up, especially in the cases, in practical cases, you will have lots of implications as well, like, and you want to kind of sew them together. So the question is, how, in what order do you want to apply the proofs? And if you want to use an implication, if you start proving an implication too early, then all the work that you do is basically for nothing. So there's all these kind of things. So instead of doing a bottom-up search, we want to go to a top-down search, where we accumulate a true sequence or provable sequence that are relevant to proving what we want to do. Now, there's the general results that you can apply the inverse method whenever you have a decidable sequence calculus. So we can think of that as a basis, and then further optimize certain checking whether you can do certain derivations by actually using the cut rule. And I don't have too much time, but the whole idea is that you may have lots of multi-premise rules to make a derivation. And every time that you have a multi-premise rule to make a derivation, you will need to look through the entire database of true sequence to make the derivation and then check whether it matches. So one solution to that is to only have one rule which has two premises in that sense, and that's the cut rule, and just make sure, almost like prologue style, that every pairing up we have its cut, and then we just go through the entire database of sequence. So we start with a set of questions or goals, which we mark question mark A. We have a set of answers or assumptions, well, I call them answers, or possible assumptions, which I write as bang A. And then in forward proof search, we'll have two phases. First, you have an initiation phase, which recursively looks at what you want to prove and what you want to use to prove this, and spins up more questions and relevant sequence to prove them. And then the accumulation phase, which will apply cuts and other rules in order to find the other true rules. In order to deal with modalities and disjunctions in an effective way, there's two alterations that I make. One is that I use multi-consequence. So we have multiple consequence in order to more effectively deal with, the disjunction rule is quite cumbersome to check every time that you can combine disjunctions. So I use multi-consequence here, and then also special form sequence where we, like when we almost Fitch style, separate the context into two contexts separated by modality, by which we mean this, that given all phi, then within M, this sequence holds. And then the cut rule, we kind of extend, we need a basis of modalities which cover both M and N. So then we can have a general cut rule where we have an A here and an A here, and then we cut into there. But in order to make it more flexible, we want to have a kind of a general, the down diamond is kind of a lattice style operation on your modalities. That includes identity because we have necessity, so we can always, if we have a sequence of this, we can always make this an M because of necessity. So these are all the rules. So like I said, initiation, we have questions and assumptions. We generate relevant sequence and more questions and assumptions until we're done with that. And then during the accumulation, we make cuts. We check for, and we need separate rules to deal with implications and modalities. All right, this is maybe a very quick example. So let's suppose that we have the box modality and we want to prove from box A and box of box A implies B, box B. What we can do if we just search or if we just work with the decidable sequence calculus, we can use the mod rule. So we look at what's readily available. So we get box A, this one, and the unfolding of box A. Can do it again. Actually, in this case, the context doesn't change. And now to prove B, what we do, well, we first prove box A in order to get the B here. And these are both by the identity theorem. So this is when you search bottom up. But if you search with forward search, we'll have question, when is box B true, given that we could use box A and box A. Box of box A implies A. Where is the second one? In this one or not? Yeah, there. Yeah. So we still want to prove box B here. So we can again do the mod. So we do box inverse of this, right? So we can go through every formula here. So again, this box A will make a box A and A. Well, this A is not in box, so this gets discarded at this point because it's not ready. Yeah, it gets replaced by this A again. Yeah. Okay. Yeah. But the subformula properly holds, so that's the important thing. But we can think of it going down as well. So from box A, we know that box A, then within box A, and box A, then within box A. These get spin up, and then you effectively create your cuts in order to see if you can prove these mod rules. Now, some final remarks. I want to say this is certainly not complete final remarks. I have a lot more final remarks given that all the talks that I've seen today, so I'd love to talk to a lot of people. So first of all, I have a Haskell implementation. It's not out yet, but it's just where you You can type in some assumptions in the question, and then it will spin up a proof. This proof is like, should be readable in the kind of lambda, what is it, multimodal dependent, well, type theory style. I did a crack on some visualization of applying different cut rules in sequence, just to see how these proofs kind of generally generate. Now there's some logic extensions. These were very last minute when I was writing the paper, but you can actually also add consistency axioms. So if you have M false, then it's false, by adding a particular rules, and unitality axioms when you want to actually have X implies MX. There are some situations that are complicated, and I'm wondering if there are solutions to that, which is the reverse. So if you have Mn of A going to Ra, going down, or if you skip a modality, so if you go from A to Mna or the other way around, which I've seen in the kind of tense logics, I think, right? You may have that. Yeah, so another thing I was thinking of doing, generating counter models, but that's for future work, and exporting it to kind of modal dependent type theory as well. And I think I'll leave it there. Thank you.
Thank you.